Okay, so for chapter 11, all of the things that we learned in chapter 9 sort of went into chapter 10, right? We learned electronic structure in the atom and what happens if there's an ion, right? Electrons either lost or gained. And then if there's covalent bonding between nonmetal and nonmetal, what does that look like? That was chapter 10. So looking at Lewis structures. Chapter 11 is going to continue, right? I think I had mentioned chapters 9, 10, and 11 are almost just like one big topic. So we started with the atom, then we looked at bonding, ionic and covalent. Now we're going to go further and look at structure. So when all the things we did in chapter 10, we got to know how to do in chapter 11 as well. So the good news is if you like this material and it comes sort of naturally to you, then then that means you got 3 chapters of good material that comes naturally to you. If you're like me and you would much rather just do math problems all day and sort of the spatial reasoning of all this is a little bit more difficult, then it might be a bit more of a challenge and just practice is key. But I I sort of teach this in a way that I would learn it best, and this is not how it was taught to me. But if in me, from my mind, this is how it makes sense. So hopefully I do a good job of making this easier than it was for me. So with VSEPR, valence shell electron pair repulsion. So VSEPR theory is now that we understand covalent bonding and we understand when is a double bond appropriate, triple bond, et cetera, and we understand formal charges to come up with the best possible structure. And we've started to talk about expanded octet. Now what we're going to do is we're going to look at what that structure looks like. And we have to be able to think three-dimensionally here. And as I mentioned, that's a bit of a struggle for me. And like I'm going to try to draw some three-dimensional structures for you today, and it's going to be terrible. It's just not something I'm very good at. You will probably do much better than I. However, there is no requirement for you to draw three-dimensionally. So I'm going to do my best, and that's all I can do. All right. So first thing is when we're looking around the center atom, and everything with VSEPR theory is always talking about what does it look like on the center atom? Are we looking at two things bonded to the center atom in a straight line? Or are they in a bent angle, right? Those are the kinds of questions that we're going to start looking at. And I'm getting my book handy so that I can also show you structures using my book rather than my drawings. So when we go through chapter 11 questions, I'm going to assume that everything we did in chapter 10 is still at the ready. All right. So when we look at carbon dioxide, CO2, we learned carbon would be the center element because it's less electronegative. We would end up with 2 double bonds here. We did CO2 in the previous chapter, so that's why I wasn't going to go through the time of doing it. I will do it with some of the future compounds so that we review it. We end up with 2 lone pairs on each of those terminal oxygens. And remember, our electron count, right, goes to the group number. Carbon comes in with 4. Each oxygen comes in with 6. So there should be 16 electrons here. 2, 4, 6, 8, 10, 12, 14, 16. So that is what we did in chapter 10. Now let's do chapter 11. Chapter 11 is this VSEPR notation of AXE, right? That's what we're looking at. N refers to the number of bonds. And what's interesting is a single bond counts as 1, a double bond counts as 1, a triple bond counts as 1. So basically just how many elements are bonded to the center element. And then E is the number of electron pairs, right? So M, that subscript on the E, refers to the number of electron pairs, and it's always on the center. We're always looking at what the center element looks like. Because basically the question we're trying to answer is this going to be a straight line? Is it going to be bent? And we're going to really, the only way we understand that is if we know what the center element looks like. So in my notation, right, the A is just referring that there's a center here. So that's carbon, right? The carbon's the center. The X is how many bonds there are. So I'm going to try my best to color code this, hoping that that might help. So I have 1 bond and another bond. So that's why it's a 2, AX2, right? And again, like I mentioned, it doesn't matter in the terms of the X, the number of bonding elements, It doesn't matter if it's a single bond, double bond, triple bond, it all just counts as one for the X. So there's 1, 2, right? So AX2. And then the E in this case is the number of lone electron pairs on the carbon. And in this case, this would be a 0, right? And so I'm going to make a little note because there are no lone electron pairs on the center carbon. All right, so sometimes students will say, well, but there's these lone pairs on the oxygen. Don't worry about those. We're always just looking at the center, always looking at the center element. So what valence shell electron pair repulsion theory says is that when I look at these electrons around the center element, whether they are bonding pairs or lone pairs, remember electrons repel. So they want to get as far away from each other as possible. So what is that geometry going to be? How do we best maximize the space between this bonding, well, two pairs, right? But that's okay, double bond, and this bonding 2 pairs. And so this is what you're going to do in lab on Thursday. You have your carbon center, and it will have a double bond to an oxygen, and then another double bond to an oxygen. When I look at this, right, there's 2 geometries that we can talk about. There's an electron group geometry and then a molecular geometry. And we'll do that distinction more here in just a little bit. But you can see why this geometry is called linear. Because if I just look at the molecule, like what do I see? I see carbon, 2 oxygens in a straight line. To best maximize that space between these bonds is 180 degrees. Can't do any better than that, right? So AX2 with no E, right? When there's no E, you can just leave it off. It is like I put E0 here just to show you that there's no pairs on the center. We're always looking at what the center element looks like. So normally you would just write this as AX2. You leave the E off unless there's an E that you need to note in the notation. And so that's a linear geometry. And what that means is when I look at this, the carbon, oxygen, right, this right here, those 2 bonds, right, that is a full 180 degrees. And that's the best bond angle we can do to maximize the space. So that 180 degrees maxes the space between the 2 double bonds. All right, and that's VSEPR. Valence shell electron pair repulsion theory is that we want to maximize the space between any electrons around the center element. Everything's going to be in pairs. When they're not in pairs, remember those are free radicals and they're very rare. So everything's going to end up being paired here. So let's try another one. We've got silicon tetrachloride and we're going to do antimony pentachloride. All right, so the silicon tetrachloride, SiCl4, silicon less electronegative, that's going to go in the center. And then we're going to have chlorine on 4 sides. All right. And when we were doing Lewis structures, we talked about only having 4 bonding elements, right? Because we're kind of thinking about this sort of AX4 notation as sort of the maximum, right? You have a center element, you've got up to 4 bonding elements. We did touch on expanding the octet, but we're going to have to do more of that in this chapter. But the idea when we first started Lewis structures was that you have sort of your center element and there's up to 4 bonding sites, right? Because that matches the S2P6 configuration. So there's my silicon symmetry. We've got chlorine on those 4 bonding sites. If I go and add up all of my electrons, silicon is group 4, just like carbon. Chlorine is group 7. Since there's 4 chlorines, that would be 28, plus another 30, plus another 4 is 32 total electrons. All right, now I've got 8 so far in those 4 single bonds, which means I've got 28, which means I have 28 plus 4, so 32. I've used 8 in those 4 bonds. And that means I've got 24 left. Sorry, my math, I was trying to do too many things at once. All right, so silicon looks good, right? We talked about how you want to get to that octet. And so we have a full octet for the silicon. It's got a full 4 bonds or 8 electrons around it. Each of those chlorines with only 2 electrons around it so far, they would each need 6 more. So if I go through and say, okay, each of those chlorines needs 6 more, so there'd be 6 more, 6, 6, 6, that would be 24 needed. And then we talked about when, the number left and the number needed is the same, this means we've got the correct structure. All we have to do is place the lone pairs. So I would put 3 lone pairs on each of those chlorines to finish out the octet. Silicon looks like it's done with the octet. So overall, this structure is fairly straightforward, right? We didn't have to worry about a polyatomic ion, changing the number of electrons, anything like that. So in terms of what we've done so far back in chapter 10, this would be getting the correct Lewis structure. If we go and look at all of the formal charges, they're all 0, right? Silicon comes in with 4. We've assigned it 1, 2, 3, and 4. So silicon formal charge is 0. Each of the chlorines look the same. They come in with 7. We've assigned it 1, 2, 3, 4, 5, 6, 7. So in this case, all formal charges are 0. So that's another indication that we've got the right structure. Sorry, that came out as like an N. That's supposed to be an R. So all formal charges are 0. All right, now let's talk about the chapter 11 part of this. Okay, so now that we've got the Lewis structure, now let's link it to VSEPR. So if I do the VSEPR notation here, right, the silicon is always what we're looking at. That's my center element. That is quote unquote the A, right? We have a center element here. Now the X is the number of bonding elements, right? So we've got 1, 2, 3, 4. So AX4. And then the E again is the number of lone pairs, but only on the center, right? And silicon doesn't have any lone pairs. So we're always just focusing on that center element, because what we're trying to understand is, what is the geometry of this molecule? How do I best maximize the space between this bonding pair and this bonding pair and this bonding pair and that bonding pair, right? So we're always looking at the center element to understand the geometry, like what does the structure look like? So when you have AX4, right, we talked about if there's no E, you just leave it off. So this is AX4 notation. If you look at it in a 2-dimensional way, like in the plane of the paper, you might guess that each of these bond angles are 90 degrees. Because, right, that would make 360. So you got 90, 90, 90, 90. Then it turns out the bond angles here are about 109.5. And don't ever memorize the bond angles. There's no reason for you to know that. So what happens is you actually, you get a structure like this. All right, so it almost looks like you've got this like triangular pyramid base, and then there's one sticking up here. So these 3 at the bottom, it's almost like a pyramid, right? And then there's the one sticking up at the top. So this geometry is called tetrahedral. So this is your tetrahedral shape. And what I'm doing is we have to be able to do it 3-dimensionally. Like you think about this 3-dimensionally, is we don't have to work within the plane of the paper. If we look at this 3-dimensionally, right? Now what I see is if these 2 are in the plane of the paper, right? Like if I kind of try to hold this where this is in the plane, then I have one going back and one coming out. So these 2 right here are in a plane. And then you have one going back and one coming out at you. And that maximizes those bond angles. And it makes sense that each bond angle would be the same, because they all want to be equal distant apart. So tetrahedral, you end up with 109.5 as your bond angle. So I got the balls and sticks because I was kind of hoping that that would be a good way of showing you. But if I look in the book, right, here's another one. All right, so again, you kind of have these right here in the plane, and then one going back into the paper and one coming out at you. All right, so when I was doing this as a student, we had sort of thick curved lined and dashed lines, and this book doesn't really do it so much. So then we don't really have to worry about it at all, which is nice. So if you're good at 3-dimensional drawing, which as I mentioned, I am not, you would maybe say, okay, here's my silicon, here's the chlorine, here's the other chlorine in the plane of the paper. And then I have one of these chlorines kind of going out and back away, and one of them coming out into the front. So like one's coming out at front and then one's going back into behind the paper. All right. The three-dimensional drawing for me was not helpful because I'm not good at it. You might be great at it. So that might be something that helps you. But the main point is that it's not 90 degree, 90 degree, 90 degree because we're not limited to two-dimensional space. We have a three-dimensional space. So all I need you to know is that AX4 is tetrahedral. And I'll show you exactly what I need you to know and not know. So with silicon tetrachloride, what I would hope you would be able to do is number one, get the correct Lewis structure. Once you have the Lewis structure, assign the VSEPR notation, right? So X4, because there's 4 bonding elements without an E. And then I'll need you to remember that if it's AX4, it's called a tetrahedral shape. Makes sense? 4 tetra, right? So that makes sense. And then AX2 makes sense because it's in a straight line. So that would be linear. So those 2 geometries I need you to know. There's another one here for us to do. It's antimony pentachloride. So this is going to kind of blow apart the 4 bonding sites, right? Everything we talked about with chapter 10, like we touched on expanded octet when you had extra electrons. And this is going to change that geometry, right? Because when you have 5 bonding elements, we obviously are not going to be limited to just the 4, up, down, left, right. So in this case, we're going to have our antimony in the center. And we're going to put chlorine and chlorine and chlorine. And then I'll show you, I did that backwards. All right, so we won't worry about that. All right, I'll show you the structure here in just a little bit. All right, antimony is group 5, same as nitrogen, phosphorus, arsenic, comes in with 5 electrons. Each of those chlorines, again, come in with 7. Since there's 5 of those, right, we got 7, 7, 7, 7, 7, 35 plus 5, we got 40 total electrons. Now, I've used 10 electrons in those 5 bonds. So I have 30 electrons left. And the center element looks like not only is it full, but it's over full, right? We have 10 electrons around the antimony. Let's make sure that's okay. Now, antimony right here, we know it's row 5, so it definitely can expand the octet. Yeah, I find those drawings confusing too. Anyway, I was reading the chat. So the 30 electrons that are left makes sense to complete the octet. We're going to need 6 more on each of those chlorines, and that would be the remaining 30 that we have left. All right, so chlorine each to finish the octet. Octet needs 6 more electrons. There's the 30 we had left. So again, there wasn't any need for double bonds here because we had enough electrons to go around to complete the octet for each of those chlorines. So this structure looks like this. So I tried to have all these ready. Okay, so if I imagine, this is what I was trying to draw. Here's my antimony center. Here's a chlorine and a chlorine. That's this chlorine and this chlorine. This one right here would be kind of in the plane of the paper, or maybe I'll do it this way. All right, so there's my straight plane. This right here, these 3 are in a plane. They're in a straight plane. Then I've got one going back and one coming out. So if I'm looking at bond angles here, and again, you don't have to memorize these, but this is the best way I can maximize these out. Bond angle between the top and the bottom is a full 180. And then if I flip it this way, between these 3 that are in that center plane, they're 120, 120, 120. So if you try to draw this, more power to you. But for me, I've got chlorine on top, chlorine on the bottom, chlorine in the plane right here. This is a straight line. That's this chlorine. And then one going back into the paper and one coming back out at you. Now, do you really have to draw 3-dimensionally? No. It just might help you. If you're more of a visual person, it might help you to be able to do that, but you don't have to do that. So with the notation here, again, that's what I need you to be able to do is the VSEPR notation. We always focus on that center element, the antimony. That's my quote unquote A. There are 5 bonding elements, right? 1, 2, 3, 4, 5. And again, no lone pairs on the center. So that just sort of simplifies to AX5. And that notation, which I need you to remember, is called trigonal bipyramidal. And then for trigonal bipyramidal, I'll show you why it's called that, because some of these actually make sense. Why why they're called that. I'll get to the one that doesn't make sense here in just a minute. So if you look at this, right, imagine here's my plane, right, in the middle. This right here, oops, sorry. This right here would make a pyramid, right? You've got a top and a 3-part bottom, like a triangular pyramid. And then if I flip it, right, I have another pyramid. So it's trigonal bipyramidal, 2 pyramids, right? You got a pyramid on the bottom and you got a pyramid on the top. So trigonal bipyramidal is AX5. So I'm trying to highlight what I need you to remember. And that's trigonal bipyramidal because again, you've got the triangle in the center, like those 3 that are in the plane. If you look at it from the top, there's these 3 and they make a pyramid on the top, right? And then they make a pyramid on the bottom. So it's like a pyramid and an inverted pyramid squished together. I know I don't do a very good job of explaining 3-dimensional things because it's just not, I'm so much better with math. But anyway, if you can come up with the Lewis structure, which is great, the VSEPR notation, which is great, and then memorize trigonal bipyramidal, you're golden. Okay. So the next one we've got is sulfur tetrafluoride. So SF4. Question is, why is that not tetrahedral? Right? If I'm looking at silicon tetrachloride, that was tetrahedral, right? We had the center silicon right here, the black one, right? And then we had 1, 2, 3, 4 chlorines. That was that tetrahedral shape. But the question here says, okay, sulfur tetrafluoride, which looks like it would be similar, right? SF4 instead of SiCl4. Why is that not tetrahedral? So now what we got to do is do the Lewis structure. So we're going to do a sulfur center. We're going to have fluorine on 4 sides. We'll worry about the 3-dimensional part here in just a second. When I go and count my valence electron, sulfur comes in with 6 because it's group 6. Fluorine comes in with 7. There's 4 of those, so that's 28. So I have 34 electrons total here. And that might right there be enough for you to see the difference. When we were looking at silicon tetrachloride, we only had 32 electrons. Now we've got 34. Where did the extra 2 go? All right. So when I look at my structure, I've used 8 so far. So I've got 26 left. When I look at who needs what, right? Sulfur looks like it's full, 2, 4, 6, 8. So each of those fluorines would need 6 more to complete the octet. So 6 times 4 would be 24. And so we did see this back in the last chapter. We've got 2 extra electrons, and those are going to always go on the center. When you have extra electrons always go on the center element. So this is going to tell us what's going to happen and why it's not tetrahedral. So I would have my 3 lone pairs on each of those fluorines to finish out the octet. Fluorine cannot expand the octet, so we know we can't do anything more than 8. So those last 2 electrons that are extra are going to be sitting on the sulfur. The sulfur can expand the octet because it's a row 3 element. So again, making sure I've got 34 electrons here. We've got 8, 16, 24, 32. There's my 34. That right there is where VSEPR comes in. And it says, okay, well now the 109.5 bond angle, like we saw with tetrahedral, that's not going to work because yes, I've got those 4 bonds, but now I also have that lone pair. And that lone pair repels the bonding pair just like the other bonding pair. So that has to have its own space too. So what happens is if you look at the VSEPR notation here, you have AX4E, and that's why it's not tetrahedral, right? And the E is the number of lone pairs. So we only have 1 lone pair on the sulfur. Now, what happens is we have a distinction between what's called an electron group geometry, blah, 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 and a molecular geometry. So, and the lab will definitely make you sort of focus on this quite a lot. Okay, so first, 4 plus 1 means there are 5 total electron groups, right? So we've got 4 as bonds, 1 as a lone pair. All right, so I've got 5 total groups around the sulfur, right? 1, 2, 3, 4, and 5. So what happens is that if it's got 5 total groups, it actually should look a lot like the AX5 because that had 5 total groups, right? So with the molecule, when I'm looking at the geometry, the electron pair doesn't matter. They don't care if they're repelling a bonding pair or a lone pair. A pair of electrons is a pair of electrons. So the 1, 2, 3, 4, 5 bonding pairs behaves very similarly as 4 bonding pairs and a lone pair, right? So there's an electron group geometry. And the electron group geometry is that since there are 5 total electron pairs around the center element, right? The 4 plus 1, the 4 bonding pairs and the one lone pair. That means the electron group geometry, which I call the egg, is trigonal bipyramidal, just like that antimony pentachloride that we saw in the previous paper, right? It's still going to look like the AX5 in terms of the shape of it, right? The shape of the electrons, I should say. So what you're dealing with is when we had antimony pentachloride, right? We had one of these. This was our antimony pentachloride. We had the pyramid pointing up and the pyramid pointing down at the bottom, right? And that was our 5 total electron groups around the center that explained the bond angles. So the electron group geometry is trigonal bipyramidal. What's different here is that for the sulfur tetrafluoride, the one we're looking at now, is that we instead, actually, let me change that really quick. One of those bonding pairs is just a lone pair. Everything else is the same. We still have those 4 halogens, right? But one of those, like we had on the previous page with the pentachloride, one of those is now just the lone pair. That's this lone pair on the sulfur. But it started out with this electron group geometry with 5 total groups, and that was trigonal bipyramidal. Now what we're looking at is the molecular shape. So there are 2 things for compounds. There is the electron group geometry and the molecular shape. The electron group is the total number of groups around the center, all right? And of that, there are only 4 main electron group geometries. This was on the very first page. Sorry, there's 5. AX2, AX3, AX4, AX5, AX6. And I'll show you all those here in just a second. All right, so we looked at linear. That was the CO2. We looked at tetrahedral. That was the silicon tetrachloride. We looked at the trigonal bipyramidal. That was the antimony pentachloride. But these electron group geometries are when you have AX2, AX3, AX4, AX5, and AX6, right? That's where we max out. Now, if one of those electron groups is not a bonding pair, but a lone pair, okay, then the molecular shape is going to be different. So what's the difference? The electron group geometry, right, the egg, is how all those electron groups are oriented in space, right? Like what are those bond angles between all of those groups? So the electron group geometry is just the total number of electron groups that you see. All right, so that is where you have 5 total groups. It's trigonal bipyramidal. The molecular shape, right, is what the molecule actually looks like. Like if we could see the bonding elements here and we could actually see what the structure looks like, we wouldn't see the lone pair. We would just see the sulfur and the 4 fluorines, right? You know, if you could just look at the molecule in an electron microscope or in a molecular microscope, we're not going to see the lone pair. We would just see those bonding elements and the sulfur. So the molecular shape here, I know it's hard to see on my camera, but it's actually called seesaw because that's exactly what it looks like. So you got this base here and these 2 kind of going back and forth like a seesaw. So the molecular shape is just the balls, right? That's what you would actually see. So what is that shape? And this is called seesaw. So I'm going to shoot down here because this was some of the questions that came in on the chat. All right, expanded octets, you are correct, can only happen when you can tap into d orbitals. And since sulfur is row 3, it does have access to a 3d, right? We just said it's not possible when you have a row 2 element. You can never expand the octet on nitrogen, oxygen, fluorine, or carbon. But silicon, you can expand the octet. Sulfur, you can expand the octet. Bromine, antimony, anything that has a D in that subshell or in that energy level. So if N is 3, you have 3s2, 3p6, and a possible 3d10. You can have a 3d here. So we can expand the octet on the sulfur. Couldn't do it for the fluorine, but we can only do it on the sulfur. So that was one question. The extra electrons, when we're doing this, if you go through your VSEPR and you go through all your electrons and you end up with extra, they're always going to go on the center. So that's another question that came in. And the VSEPR table, this is what I'm going to have for you on the VSEPR for the test. All right. So, and this is for the same for my lab students as well. So this is your VSEPR table. Anything I have in bold is what I need you to remember, and I'm going to highlight it just so you know for sure. And I put a star next to it on the table. I need you to know the 5 main electron group geometries. So we had said AX2, that was the carbon dioxide example, that's linear. AX3, I'll show you in just a little bit, that's trigonal planar. AX4, that was the silicon tetrachloride, tetrahedral. AX5, that was the antimony pentachloride, the trigonal bipyramidal, right? The 2 pyramids. And one that we haven't looked at yet, which I never understood, AX6 octahedral. Like that seems like a missed opportunity. Why not hexahedral? But whatever. AX6 octahedral. Those are the 5 main electron groups. All right. Now, molecular geometry. All right. Here's the thing. If there are no lone electron pairs on the center element, then your molecular shape or geometry is the same as the egg, the electron group geometry. So if I had my silicon tetrachloride, there were no lone pairs on the silicon. It was an AX4, no E, right? So the egg, the electron group geometry is tetrahedral because there's 4 bonding elements, but there's also no lone pairs. So what we see is still tetrahedral, right? With the trigonal bipyramidal, the AX5, that was the antimony pentachloride, which had no lone pairs on the antimony. So the electron groups, we had a total of 5 bonding pairs of electrons. So that is a trigonal bipyramidal electron group geometry, and it's a trigonal bipyramidal molecular shape. But when we had the AX4E, which was the sulfur tetrafluoride, now what happened here is we had a lone pair. So one of those bonding elements was replaced with the lone pair. So the distinction is with Seesaw, the electron group geometry, right, the egg, is still trigonal bipyramidal. But what the shape is, the actual shape of the molecule, is the seesaw. So if you look at the chart, this is how it's going to be. If you look at the number of groups, you'll see that they're all linked together, right? If you have 3 groups, if you have 4 groups, let me color code them. Okay, then you can have 5 groups total, and then you can have 6 groups total. If you have 6 total groups, your electron group geometry is octahedral. If you have 5 total groups, your egg or electron group geometry is a trigonal bipyramidal. If you have 4 total groups, your electron group geometry is tetrahedral. All right, so what does that show you? When they're listed in order this way, and this is exactly how the table will be listed. Whatever the first thing is here, the AX3, that is the molecular shape, trigonal planar, and it's the electron group geometry, trigonal planar. If I go to AX2E, the shape will be here. It'll tell you the molecular shape is angular or bent. The electron group geometry would still be trigonal planar. When I had AX4, we saw that was tetrahedral. That is both the shape and the electron group geometry. If I have AX3E, the electron group geometry is still tetrahedral, right? But now what do we actually see? We see trigonal pyramidal, right? Because what happens on that one, this is my tetrahedral shape, right? This was the silicon tetrachloride, right? Well, that's the tetrahedral shape. That's what I see. That's the number of 4 electron groups. If one of these, though, becomes a lone pair, and now I have 3 bonding elements and a lone pair at the top, we wouldn't see the lone pair. So when you look at the structure, just looking at the actual elements and how the structure, the molecular shape of it, that's why it's trigonal pyramidal, right? Because it's just a pyramid with a triangular base instead of like a square base. All right. If I had another one removed and I had 2 lone pairs, this is your water molecule, right? So water, 2 lone pairs on the oxygen. So the only thing we would see is the H2O, right? That is an angular or bent structure, right? It's not a linear, it's bent, but it still has 1, 2, 3, 4 total electron groups. So the electron group geometry is still tetrahedral. So the electron group geometry helps explain all the bond angles, but the molecular shape or the molecular geometry is what it would actually look like, right? And if we're looking at water, water's just a bent molecule, oxygen center, hydrogen on 2 sides, but not 180-degree linear because of these 2 lone pairs that are repelling against these 2 bonding pairs. So the shape of water is a bent molecule. So the shape, right? This is what you would actually see, right? So this is what you see the compound structure. The electron group geometry is how many total groups are there. All right. So if I go back to one more question here to help sort of review this. When we look at the next one, why is chlorine trifluoride T-shaped and not trigonal planar? Okay, so chlorine trifluoride, we have ClF3. So we have a chlorine center. Trigonal planar would be this here, right? That all of those are in a plane. We have a nice 120-degree bond angle all the way around. Let's go look at our electrons. Chlorine comes in with 7. Each fluorine comes in with 7. So that's 21 plus 7. We got 28 total electrons. All right. So we've used 6 in those 3 bonds. So I have 22 electrons left. All right. When I look at each of the fluorines, they have 2. So each of those would need 6 more to get to 8. Chlorine kind of looks like it only needs 2 more, right? So if I look at fluorine needed 6 more to complete the octet, chlorine only has 3 bonds, so it would need 2 more to complete the octet. So 6, 2, 6, and 6 is 20 that would be needed to complete the octet. The 2 extra electrons are going to go again on the chlorine. Number one, they can't go on fluorine because fluorine can expand the octet, but they typically always go on the center element, which in this case is the chlorine. So I'm going to start again over here. So what we end up with is, actually, let me do it this way. So, well, I was going to try to draw it 3-dimensionally, but it's not going to help you anyway. So we're going to have chlorine bonded to fluorine, 3 lone pairs. Then we're going to have another fluorine, 3 lone pairs, and then another fluorine with 3 lone pairs. But then what happens is we actually have 2 lone pairs on the chlorine. So if I count my number of electrons again, right, there should be 28. We have 8, 16, 24, 26, 28. So there's my 28 electrons. Remember, always go back, make sure. We expanded the octet on chlorine, which remember we can do that because that's a row 3 element. So it does have access to the 3D. All right. So when I look at my egg versus my molecular shape, okay, so when I do the VSEPR notation first, I have AX3 because there's 3 bonding elements around the chlorine, 1, 2, 3, and then an E2 because there are 2 lone pairs. So if I look at the 2 types of geometries, the egg, right? How many total electron groups are around the chlorine? 1, 2, 3, 4, 5. Okay, so 5 total electron groups. So that means it would come under, right, sort of the AX5, the 5 total groups, right? So that is the trigonal bipyramidal. That's the one I want you to remember, trigonal bipyramidal. And I'm running out of space. Okay, sorry. So trigonal bipyramidal. The molecular shape or molecular geometry, that you won't have to memorize. You're going to come down here to the chart and you're going to say, okay, well, this is AX3E2. You find that notation right here. AX3E2 is called T-shaped. So the molecular shape is called T-shaped. All right, why is it T-shaped? When I look at that, remember the AX5 that we started with? 1, 2, 3, 4, and 5, right? But if now I've got 2 lone pairs, right? Now you can see why it's called T-shaped. So it's like a sideways T. We'll do it that way. There's my T. There's the shape of the T. Lone pair, lone pair. So this is my chlorine. 1, 2, 3 fluorines, 1 lone pair, and another lone pair. All right, I drew it this way. All right, but either way, you've got the 3 fluorines here in a plane, right? This one and then this one here. And these 2 lone pairs, which again do the same job repelling, just like if they were bonding pairs. So instead of this being a bonded element, it's just a lone pair, but it does the same thing to the structure, right? In terms of those bond angles. So the electron group, right? Total groups around the center, 1, 2, 3, 4, 5. So the electron group geometry is always the max, right? The 5 with no E, that's the trigonal bipyramidal. I want you to know the 5 main groups. The molecular shape, understanding that this is T-shaped, like I had to memorize that. I don't think you need to. So I'll give you this for this chart, but I won't have the highlighted portions will be omitted. So you'll be able to get the molecular shape, no problem. AX3E2 called T-shaped, but I'm going to need you to know it's because it's in the trigonal bipyramidal family. All right, so I kind of look at these like little families, right? 3 total groups, trigonal planar family, 4 total groups, tetrahedral family. All right, so we're going to do more of these, but when you have the AXN with no E, those are those main electron group geometries. Those are the ones I need you to memorize. Okay, so you memorize that AX2 is linear. That was the carbon dioxide example. AX3 is tetrahedral. Sorry, AX4. My brain and my hand are not working today. AX4 is tetrahedral. The AX3 is the trigonal planar. Because what I was doing is I was getting ahead of myself and I was saying, okay, make sure you remember when you get to AX5 to tell them that you've expanded the octet. So when you have AX5 or AX6, now you're looking at more than 4 groups around the center element. So we've expanded the octet at this point. These right here, AX2, AX3, AX4, that's all the Lewis that we learned before we learned expanding the octet. Once you expand the octet though, that's when you get into the trigonal bipyramidal, or remember 6, octa, sort of misleading. There's octahedral. Okay, so those are the 1, 2, 3, 4, 5 main groups I want you to remember. All right, so we're going to do more of these on the next page. And we're going to talk about polarity. So previously when we talked about polar, we were looking at a bond. So if we had an HF bond, we would decide whether it was polar or nonpolar, right? 2 nonmetals, we expect it to be covalent because the electrons are being shared between the 2 nonmetals. We expect though, because the fluorine is so electronegative that that bonding pair really gets pulled more to the fluorine side and it creates a negative end and a positive end, right? And that's how we remember that it's called polar because it's like poles on a magnet. Now, this doesn't have a Vesper because there's no center element, right? So it's not like we can look at AX2 or something like that. That's just going to be linear because there's only two things there. So that there's no geometry. It's just two elements. So that's polar. Now, if we're just looking at a bond, it's pretty straightforward. Now, what happens when we look at a molecule? How do we know if the whole molecule is polar or nonpolar? So the example I want to kind of show you is we did carbon dioxide earlier, right? We had the carbon center, oxygen on either side. This was AX2 linear, so everything's in a straight line. If I think about oxygen being more electronegative, the oxygen's going to pull the electron density in this away from the carbon, but the other oxygen is going to do exactly the same thing because it is the same electronegativity. So what happens is that even though you're playing tug of war here, we're not looking at just the bond anymore. We're looking at the entire molecule. So we're getting a strong pull to the right and an equally strong pull to the left. When that happens, overall, even though you could have a polar bond, you can have a non-polar molecule. So that can be a little confusing at first. So what we're transitioning into is looking at the entire molecular structure. So before, when we brought up polar versus nonpolar, again, we were just looking at a bond. And we were like, okay, oxygen's much more electronegative. It's our second most electronegative element. So that bonding pair of electrons wouldn't be shared evenly because it'd be pulled more to the oxygen side. But that's just looking at those two, the carbon and the oxygen. If I expand out to look at the whole molecule and I recognize that there's an equally strong element pulling in the opposite direction, now what I'm looking at is playing tug of war, not just between these two, but between basically these two, the two on the ends, the terminal elements. And since those are the same element, the pull is the same. So that's going to mean there's no poles here. This is a non-polar structure. All right. Now, when does that happen? All right, I'm going to give you the generalizations here in just a second, but let's look at another molecule first. All right, CF4, carbon tetrafluoride. We have carbon in the middle, fluorine, and fluorine, and fluorine, and fluorine. All right, we won't worry about the lone pairs here. So we have AX4. This is tetrahedral. Now, again, kind of to reiterate what we looked at, because there's no lone pairs on the carbon, right? It's just AX4. That is both the electron group geometry and the molecular shape. Okay, so they're both the same. Tetrahedral would be the answer for both of those. If I ask you, okay, CF4, what's the electron group geometry? You'd say, okay, 1, 2, 3, 4 total groups, tetrahedral. If I said, what's the molecular shape? There's no lone pairs here, so it's going to look exactly like tetrahedral. Now, polar versus nonpolar. If I look again at just the carbon-fluorine bond, the bond itself would be polar. All right, but that's only looking at the bond. What we're focusing on now is the entire molecular structure. So the molecule overall is nonpolar. That's what we want to focus on. So you might be looking at that and being like, how do you get nonpolar from that? So let me go back and put all the little balls right back on this. So this takes me back to physics, right? So kind of the idea of for every force, there's an equal and opposite force, but it's a little bit different here. But again, this is where three-dimensional thinking really helps, which again, this is why this was so hard for me. We're pulling up, right? Fluorine is our most electronegative element. So we are pulling electron density up with that fluorine. However, I've got 3 fluorines that are pulling out and down. When you have a symmetrical molecule with no lone pair, Okay, that's going to be the key. When there is no lone pair, the idea is that every force, right? The most electronegative is always on the end. Every force, there is an equal and opposite force. It's not as easy to see as linear because then it is truly left, right, even, right? But this fluorine is pulling up. These are pulling out and down. And I know they're at an angle, but that downward pull of those three equals the upward pull of that one fluorine. The one that's pulling off to the left-ish is being offset by these pulling to the right-ish. Okay. So the idea is that if you have an AX3, AX4, AX5, that molecule is set up to where all those bond angles are the same because we're trying to get to symmetry, right? We're trying to maximize out all of those distances between the bonding pairs of electrons. So when you have an AX4 with no E and all terminal elements are the same, it will be nonpolar. All right, so I'm going to make a little note up here at the top. All right, when you have AXN, right? No E. You can't have any lone pairs, although there are two exceptions because there's always exceptions. And I'll show you what those are. When you have an AXN, okay, and all terminal, meaning the ones on the end, elements are the same, it will be a nonpolar molecule. All right. So there will be no poles. All right. But this is the thing. It has to be AXN and all the terminal elements have to be the same. Okay. So what do I mean by the terminal elements? Okay. So this is my structure for tetrafluoride. Those terminal elements, they're all the same. They're all fluorine. If I swap one of those and I say, you know what, let me make one of those hydrogen. Okay. So now let's say this up here is hydrogen and these are my fluorines. So I swapped that fluorine for a hydrogen. Now what I'm doing is I've got a strong pull down and out and nothing equal pulling up. So if all terminal elements aren't identical, it's going to be polar. There's going to be an uneven distribution of the electron density overall for the molecule. But as long as all of those terminal elements, those bonding elements are exactly the same, then you have a perfect symmetrical structure and that'll create nonpolar. Okay, so AXN, no E, nonpolar. So CO2, AX2, no E, no lone pair, right? The two bonding elements are the same, nonpolar. AX4, no E, all bonding elements are the same, nonpolar. Okay, so this is the one I was talking about. If I have the CHF3, the hydrogen pulls up, but those fluorines, they pull down and out with much more force, right? Because fluorine is our most electronegative element. Whoop, that went flying. So what'll end up happening is if you were to look overall at this molecule, you would have a negative end and a positive end, right? So if I looked at the structure now, right, I'd have all of the electron density down here at the base with all those fluorines because they're so electronegative. They're pulling the electron density down here and the hydrogen's not pulling up. So overall, you would have a negative and a positive end. So even though it's still AX4 tetrahedral and there's no lone pair, since not all bonding elements are the same, this is going to be a polar molecule. All right. And just remember polar, like poles on a magnet. You're going to have a negative end and a positive end. Okay. So we've got a negative part with the fluorines, positive part with the hydrogens. All right. Trigonal planar. We haven't talked about this yet. When we were looking at Lewis structures, we had said there are some exceptions to the octet rule, right? Hydrogen, we saw always as a duet rule. Hydrogen maxes out with just those two electrons because it's 1s2 helium. That's all it can do. Boron was another one. Okay, so you always want to remember boron is one of the exceptions to the octet rule. And boron typically takes just 3 bonds. All right, and that's what you'll see here. It's BF3. So boron with fluorine and fluorine and fluorine. This one, it's easy to be tripped up on this one. Just remember boron doesn't do the octet because otherwise you'd end up with like double bonds here and it wouldn't be right. So to finish this, each of those fluorines has 3 lone pairs to finish out the octet. And then the boron is just going to be done with those 3 bonds. That's it. All your formal charges here are 0. Fluorine comes in with 7. 1, 2, 3, 4, 5, 6, and 7. Boron comes in with only 3. It's a group 3 element, and we've assigned it 3. So all formal charges are 0. So that's our structure. Boron is just one of the exceptions. So we would have AX3, no E. That's one of the 5 I need you to know. It's trigonal planar, not pyramidal. It's just a plane. The boron, right? If I look at it, this is my boron. It's almost like a fidget spinner that I remember from days ago. There's my 1, 2, 3 fluorines in a plane. The bond angle here is 120. We can't make that any better. Like we're just going to keep that right there, 120 degrees. So that's why it's trigonal planar, not pyramidal, right? Now, we saw this earlier. If there was a lone pair at the top, right, then what happens is you'd have your 3 bonding elements squished down because that lone pair is repelling it. So this is AX3, 1, 2, 3, E, right? That's trigonal pyramidal because it's in a pyramidal shape. This one here, the boron trifluoride, refocus, because, didn't want to refocus. Because it has just AX3. Let me kind of push it out and push it back in. Nope, still doesn't want to focus. Oh boy, I think it's telling us it's time for a break. And yeah, the question in the chat was, we're not working with any ionic compounds. And at the moment, that is correct. We are not doing anything with ionic compounds here. All right, so I am going to stop the video here really quick and then turn it back on and see if that does anything to the refocus. Nope, still didn't. All right, so let's take a break here. I'm going to play around with my camera, make sure I can get it to start working. We're a little bit early, so let's come back a little bit earlier to segment 2. So instead of waiting until 12:30, let's go 12:25. Just make sure we've got enough time for the second part. So I'll meet you back in the part 2 room at 12:25.